Hi there everybody, thank you for joining me today for this recording. I'm going to try to explain to you in a very thorough, understandable way how to prove a chain rule, which is a massive result which is needed for A-level maths for any course, Edexcel, AQA, OCR, whatever. So let's get started. But before we do, I just need to mention a result that I'm not going to prove, but I'm going to use. So before we get to the actual proof, a special note. Before we begin with the proof of a chain rule, like I say, we need to use a general result, which I'm not going to prove robustly here. It can be proven, but it's probably best left to university level, because to prove it carefully and in a watertight way, it probably goes beyond A level. But essentially, the result's this. If we've got f of x and g of x, which are both differentiable functions with a limit that exists as h goes towards 0, then we can use the fact that the limit of h goes towards 0 of f of x plus h minus f of x all over h multiplied by g of x plus h minus g of x all over h equals the limit of the derivative of f multiplied by the limit for the derivative of g. So all we're saying here is that the limit of one multiplied by the other can be separated into two separate limits. I'm just going to give you a quick illustrative example to just try to convince you that this actually does hold up. So, for example, let f of x be 2x and g of x be x squared. So dividing the page into two so we can just see if this does work. Then using this on the left hand side, then the limit of h goes towards 0 of f of x plus h minus f of x over h times g of x plus h minus g of x all over h becomes, just subbing in that f of x is 2x, we get two lots of x plus h minus 2x over h, and for the limit of g of x, which is x squared, g of x plus h is x plus h all squared minus g of x minus x squared all over h. We can expand out and then simplify these bits. This becomes 2x plus 2h minus 2x over h, and expand out x plus h all squared gives us x squared plus 2xh plus h squared minus the x squared. So we can cancel the 2x and the minus 2x here, the x squared and the minus x squared here, to give us that it's the same as the limit as h tends to 0 of 2h over h times 2xh plus h squared over h. This bit we can cancel the h's to leave us with 2, and if we divide through this second part by h, that will leave us with 2x plus h. So it simplifies to this, two lots of 2x plus h as h goes to 0. So multiply by 2, this gives us 4x plus 2h. As h shrinks to 0, 2h vanishes, so we're just left with 4x. Taking it in separate pieces now, then the derivative of f of x, as h goes towards 0, from first principles, we can just sub in that f of x is 2x, expand the brackets, the x's cancel, which leaves us 2h over h, h's cancel, and the limit as h goes towards 0 of 2 is 2 all day long, so that's just 2. Dividing this part of the page into a separate part now, we can do the same for the derivative of g of x. So, taken separately, the derivative of g of x is this. If we sub in that g of x is x squared, we get this result here. Expand it out, we get this. X squareds cancel, so we're left with 2xh plus h squared all over h. Divide through by h leaves us with 2x plus h only. So as h goes towards 0, we're just left with 2x. So let's see if this result holds. So looking at the left-hand side, what we've got here on the left is this result, 1 times the other inside one limit, that gave us 4x. F of x done separately, here we got 2, and then g of x done separately, we got 2x. So does the blue times the green give us the red? Does 2 times 2x give us 4x? Indeed it does. 4x is 2 times 2x. So that's hopefully helped to convince you that this we can use and this result does hold up. We're going to use this now. So let's begin the proof proper. Before we do, let's just start from year 12, the definition of the derivative of a function y, where y is f of x, differentiated with respect to x. This is in the formula book in your exams. dy by dx is this. We can also now adapt this formula to differentiate a composite function. Sometimes it's called a function of a function. So consider the composite function y is f of g of x. Then if we differentiate f g of x, all of it, then dy by dx will be the limit as h goes towards 0, f of g of x plus h minus f of g of x all over h, whereby x is acted upon by the function g, which then in turn gets acted on by f to create the composite f of g of x. Let's just have a look at the graphs of these first. I'm going to put this in the corner because we're going to use this in a moment. That's the derivative from first principles of a composite function f of g of x. Just subbing in g of x plus h and g of x in place of just x plus h and x. So let's just consider these sketches which show the composition graphically. So first of all, x mapped to g of x. Then g of x here gets mapped to f of g of x. So the g of x from the first part gets composed onto here, then g of x goes to f of g of x. Now, for derivative from first principles, we need to take 2 points fairly close together on the x-axis. So if I call this point x, and this point here is h bigger, this will be x plus h. So x will get mapped to g of x, and x plus h will be mapped to g of x plus h. And the difference in between, like I say, is h. So when we differentiate, we need to shrink h down towards 0 to find the gradient of a tangent at a particular point. So what we're doing here, just to remind you from year 12, is something like this. So we've got 2 points, called here P and Q, and h shrinks down so that this chord becomes the tangent at the point. So that's why we shrink h down towards 0, just to recap from year 12. On the second graph, what we're going to have, x and x plus h get mapped here, and so g of x and g of x plus h we can add on to the diagram here. So this is g of x, that's g of x plus h, which then get mapped to f of g of x here, and f of g x plus h. And the gap in between g of x and g of x plus h, the difference between them, is of course g of x plus h minus g of x. So on the left-hand side, we can see here that the derivative of g of x, g dashed x, is just simply this from first principles. So it's the change on this axis divided by the change on the bottom horizontal axis, as the change on the bottom, h, tends towards 0. Now this change here is h. Over here, for the composed function, the change is this ugly thing, g of x plus h minus g of x. So if we just compare the ingredients for the derivative function of g of x, we've got g of x plus h, g of x, for 2 bits on the vertical axis, all over as the change on the horizontal axis, h in our case, tends to 0, we have this. So using this analogy, g of x plus h has an analogy of f g x plus h here. G of x is like the f g of x, and the change, which shrinks down to 0, on this one here isn't h, it's g of x plus h minus g of x. So plugging these things in, we can see that analogously that f dashed g of x is this limit here. So x shrinking down, we've got this on the bottom, and obviously the change in the vertical axis will shrink towards 0 as this goes towards 0. But this is obviously an ugly limit which doesn't look very familiar. However, what we can say is as h goes towards 0, this here will go towards 0 as well, because x plus h will become closer to x, therefore the difference in between the function values will also decrease. One will become closer to the other. So as h goes towards 0, this goes towards 0 as well, so it takes care of itself. We can just think in terms of h. So therefore, we can just rewrite this in terms of h going towards 0, because it will make this shrink towards 0 anyway. So now we've got both expressions in terms of h shrinking towards 0. What we have here is an expression for g dashed of x, and an expression for f dashed of g of x, which I'm going to put in a blue box and a red box. So we can now get to the proof properly. So those results I'm going to put over here to use for g dashed and f dashed of g of x, And we're going to start here with this derivative from first principles of the composite function. So this is exactly the same as what's in yellow. I'll just put big brackets around the whole thing. This here doesn't seem to link to g dashed or f dashed of g of x. What we do here is we make a little hack. What we're going to do inside this limit is multiply the numerator and the denominator by the same thing. We're going to multiply through by g x plus h minus g of x on the numerator and the denominator. So essentially we've got here very much a fraction multiplied by a fraction. The order we multiply doesn't matter, so what we can do here is slip this denominator over here and move the h to the denominator over here. So just switching the denominators, we now get this. So we've got this here, which we can see is very similar to results we had from before. And from the start of the video, like I said, the limit can be split into two. So if I split the limit here, we've got the limit of this thing here, which is the same as f dashed g of x, multiplied by this limit here, which hopefully you can see is the same as g dashed x. So dy by dx is therefore f dashed g of x in red multiplied by g dashed x in this blue box. And we've basically got it there. That is the chain rule. However, it's normally written in derivative notation. So in purely derivative notation, where y is f of g of x, we can write the derivative of that, f g of x all dashed, dy by dx, and use this above result. So here, we're differentiating f dashed, and y is in terms of f, but we're differentiating in regards to g of x. So this bit in red is df by dg. G dashed, though, we're differentiating with respect to x. So g dashed of x means dg by dx. So we get this result here. dy by dx is dy by dg times by dg over dx. It looks very much like a fraction where you can cancel this with that to leave with dy by dx. That's a way of remembering, but it's not mathematically watertight, but it's a useful way to remember nonetheless. Now in textbooks and notes, and even as I teach, normally the second variable isn't given in terms of g. The notation tends to be giving it in terms of u of x. So textbooks, like I say, often use u rather than g. So if we just switch the g function with u, this gives us the most useful result and more familiar. Dy by dx is dy by du multiplied by du by dx. And that is the form of the chain rule you'll encounter again and again and again. And that's all, really. That is the proof. So thank you very much for listening. I hope that's illuminated why it works and that it isn't just made up. So essentially, from me, thank you for listening. So thanks for tuning in. Do please subscribe and watch other videos if you find that one helpful. And take care of yourselves. Until next time, from Mr. Bailey, it's goodbye.